So, what is brainwaves? What is BCI? Most of people might have heard about Neuralink, Elon Musk's Neuralink, and what innovation they are trying to do. So, I'm just here to give you a brief idea what they are aiming to do, how they are able to do that, and a simple introduction in Python, then how you can leverage Python and use that information to do simple analysis to major classification tasks and different approaches. So, what is actually BCI and how you relate to brain waves? So, what you simply do is connect a brain to a device, and now that device has a job to understand the brain. Now, understanding the brain is done for two major reasons. One is either to imitate the brain or to alter the brain state. Now, you can consider imitation as, for example, a person who does not have a limb, and you are able to transform your brain signals to the prosthetic and it moves, which is something the Johns Hopkins University is doing for a pretty long time, and they've been really successful with it. And the other is altering your brain state, which is, for example, you had a tiring day at work, you go home, watch Netflix, enjoy a movie, and you're calmed down. So can this whole process of changing your brain state from a stressful to a calming or to a relaxed state, can it be done with a small stimulus, which can be an audio or visual stimulus? So this is what is altering the brain state. Now, how we are able to capture the brain waves. So if you see at this small picture, you can see two neurons interacting. So every neuron that interacts is due to a different in electric potential. Current flows when there is a difference in voltage, and when there is a considerable amount of difference in voltage, the information flows from one neuron to other. Now this is in microvolts and even sometimes lesser than that. And so how do we capture that? So a group of neurons that trigger to a stimulus. For example, if somebody slaps you, you feel pain. The whole part of the brain that experiences pain triggers itself. And if we are able to capture that mass, that is that is how we get EEG signal from the brain waves. Now, EEG, as you might have heard, is of two types. One is the simple EEG, that is the brain waves that you capture from the skull, and the other is the brain waves that you get from electrodes that are being implanted in your brain, which is IEEG, intracranial, inside your brain. As simple as that. So, how information rich is the data that we get from brain waves or brain signals, so to say. So, as far as the data from the brain waves is coming, we judge it in two manners. One is how minute effects on the brain or on your body that brain signal is able to imitate, and secondly is how real time that effect is. For example, if I'm blinking the eye, how recent my brainwave movement would be, and I'll be able to detect that change. And what all changes? Will a simple tap of the foot or flick of a finger can be detected from brainwaves or not? So that's how we measure the information richness of the brain. Now, you might have seen pictures, people wearing a huge cap and having a lot of electrodes around their head. So there's always a question, why do we need so many electrodes? So a very simple answer to that, your brain does not respond similarly to a same stimulus. For example, if I'm seeing a red color, the part of my brain that controls the auditory does not respond at all, and we don't want to capture that data. We only want to capture the data that's considered with the visual cortex, which is responsible for our vision. And hence, we place electrodes at different positions to capture different data and different reaction of the brain to a similar stimulus. So, I'll here show you an example. So, if you see this guy, he'll be blinking his eye, and the blinking of the eye is the two process. One is closing of the eyelids, and other is opening them. So you'll see a small spike down and a spike up if you focus on the top two electrodes. And as he blinks, you can see the switch. If he blinks again, you can see the switch of the brain waves. And now he will just blink once, and you see only the pitch is going down. And as soon as he opens his eyes, which I hope he'll do soon, and now. Yeah, as soon as he opened his eyes, you can see a spike coming up. So this is how real time the data is. As soon as you blink your eye, as soon as you do a very slight movement, it can be captured from the brain. This is also good, and this is also really bad. And how it's really bad, I'll explain you later in the talk. But that's how information rich the data is. So everything you do, every thought process you create, even if you think about lifting, or if I say the red color, the fact that you recall the red color is also can also be detected from the brain. This is how information rich the data is and how minutely it records. So how do we analyze this data? So first I'll give you a brief information what kind of data we get from the brain, and then we can say how we analyze the data. All right. So for every instance that electrode records data from your brain, you get a voltage which corresponds to that particular time. And generally for every second you get approximately 128 to 256 values. That means that for every second you record your brain 256 times, and that's across all the 16 channels. So it's a time series data. It's a very hefty time series data, and an analysis of this kind of data is really big issue. And that's where we need data engineers and data analyst people who can just reduce at least a small chunk of data, or at least help us localize the data and reduce the effort that we need to do. So time series data has its own properties. For example, we can see the standard deviation in the data, we can see the mean in the data, we can see other features like kurtosis, skewness, but that's not what the brain is all about. The brain is about how it thinks, the process behind the brain. And how we generally do that is generally we convert the time series data to a frequency domain. Now what's that difference? So what time series data tells you is information which can either be let's say the temperature of the day, or can be how much pollution was there at every single moment of the time. What frequency is that? What frequency domain data actually means that how much of the data was present in that frequency. For example, in EEG we have a specific set of frequencies. We have beta, alpha, theta, delta. There's also gamma, which I did mention because it's a little beyond the normal spectrum that we analyze. So yeah, so every time series data from the brain that we get, when we convert into frequency, it corresponds to a particular aspect of the brain. So if you see right here, you can see beta. Beta is when a normal human is awake and using his minds or doing some cognitive activities. For example, you're trying to understand what BCI is and I'm trying to explain it. Most probably will be in the beta stage. Alpha is when you wake up, you brush your teeth and you're relaxed. You're just thinking about what you need to do throughout the day. Now the interesting part comes is that the brain waves is constant for a particular human or to a small group of human, but it's not same across. For example, resting stage for me just might be an active stage for you, or it might just be a relaxed state for me, or it might be a very stressed state for you. So this is the uniqueness of the brain that we all possess in a way. Okay, coming back to theta. Theta is when normal human, like everybody who's like grown up here, sleeps, has a normal sleep, while it's a normal functioning of the brain for a child. And when we are in REM sleep, that corresponds to delta, mainly delta. That is when we are in a REM sleep, that is the delta for us, while it's normal brain state for a child. So this is how varied the data is. That a normal state for someone can be his sleep, other people sleeping, or other person's active state. So this is the variation that we see in the data. Now, if you look at it in a way, you can see that you can't actually create, let's say, a machine learning model or a deep learning neural network, a hefty neural network to do a proper classification, because my brain data that reflects a particular activity that I did is completely different for you. I might be having a seizure at this moment, but you might just be relaxing at that moment. So this is how varied the data is, and this is the problem that BCI faces, that it's not been able to become so mainstream in the normal community. So yeah, BCI is cool. You get brain waves, you analyze your brain, you see your brain in a way. But what problem is it solves? Like, we shouldn't be doing something if it does not solve a problem. So let's see towards the medical side how how brain waves actually help in curing, or not exactly curing, but prevention of diseases. So there's a very popular project that's been successfully done, which predicts epileptic seizure. Epileptic seizure is when a person has a very high variation in brain waves, and that causes some seizure. So brain waves, with the help of brain waves, you are able to predict that in the next 30 minutes or in the next 40 minutes, you might get a seizure. And when a person is having a seizure, that person is out of control. He just might faint. He just might have a heart attack. He might choke on his tongue. Like, anything can happen. And if you're able to help that guy 30 minutes before, that's like life saving. That's a really big deal. Parkinson's disease, again, a disease that's originated from the brain. You have different levels of Parkinson's disease, and it can also help you detect it. It can help you prevent the extremities of the Parkinson's disease. And as I explained previously, prosthetics. So let's say when I say I want to move my hand up, I pass a signal to my brain, and my hand moves up. But a person who does not have a limb, it's might have not been born, or some incident happened, he passes that signal, but nothing moves. So if you're able to encode that in a prosthetic arm, that when you receive a particular type of signal, it means you have to go up, you have to move a finger, you have to come down, whatever you need to do. So that's how you are able to imitate that. Now, the research part. Everyone, I hope, has heard of ADHD, which is like extremely less focus and hyper deviation from things. So, how is BCI able to help you in that? So, as I mentioned, neural feedback, which is, again, coming back to the example, you go to Netflix and you relax. Now, if you're able to do that with a small beep or a small sound stimulus or a small visual stimulus, that might just help you regain focus on what you are doing, and if you're able to judge if a person is losing focus or not. So whenever I'm getting distracted, a machine detects that I'm losing the focus on whatever I did. It provides me a stimulus that helps me gain that focus, and I'm again able to focus on what I'm doing, and that's how neural feedback works. And second is empathy of a person, which is something that I myself worked on, which is the level of sentiment that a person feels towards a particular thing or towards a particular incident. For example, if I show you a puppy photo, there might be a huge variation in reaction. Someone might just hate it, someone just might love it, or just chanting out different things. So what is the effect of a stimulus on the emotional state of that person? This is how we measure empathy. And that's something we can even measure from our brains, that what effects it had on your brain, or which part of your brain was affected. A cool insight that I gained from this is when we measure happiness and sad, the same part of the brain is not at all affected. There's a very less intersection part of the brain that's affected when I'm feeling happy, or at least I am, because I recorded the data. If I'm happy or I'm sad, a very less part of the brain is affected. So that was a cool insight. Again, in the industrial, consumer behavior analysis and detecting criminals. I'll come to both of these. Consumer behavior analysis is very simple. You provide a product and you get a feedback from the person. Now, expecting feedback from a person just after him or her using it for like 2 or 3 minutes is really absurd. I can't express my feelings. Obviously, if I get a new phone, if I watch a new movie, and I've just seen it like 2 or 3 minutes, I can't tell you if it was good or it was bad. But I know how your brain got triggered. Were you excited by seeing even that small part of that clip? And you even might not know that you were excited because of that clip, because you just might have had a bad day. or something like that. If you're able to map the excitement of that person for a particular incident, the empathy of that person, you can detect how happy or sad he was. Now coming to detecting criminals, this is also an ongoing research that John Hopkins University is again doing. And what the problem with detecting criminals or lie detector right now is that people are able to mask their emotion, right? So how will EEG or brainwave help to detect that? Whenever you're masking your emotion, you're sending a brain signal voluntarily to reduce that emotion. And if you're able to map that, and how you're able to map that, you provided information to, let's say, 1,000 people, and you ask them to tell a lie. And when you ask them to tell a lie, you are able to detect what part is triggered when they tell a lie. And even if they are able to succumb, or let's say if you are able to subside that feeling, they'll still be telling a lie. And if you are able to detect that, you are able to detect criminals, no matter how trained he is, because you can't train your brain. You can train your emotion, you can train the reaction that you have, you can't train your brain in a way. So these are the big problems that BCI is able to solve, and it's a very small subset of what things are being done in this field. So people are trying to imitate the learning process. So let's say you see a new word and you learn its meaning, and it's in the short-term memory of your brain. If I ask you that like a year ago, you'll probably not remember it. But if you see that word again and again, every day, every month, probably every week, you will remember it, and you really don't need to recall it. And that's the long-term memory of your brain. So people are even trying to imitate what kind of stimulus helps you put the information directly into your long-term brain rather than short-term brain. And hence, reading an article or reading something that you are preparing for an exam would be permanently embedded in your brain for a while. So that's how cool that thing is, and how weird that is that people are able to copy what you do over a month, over a week, with simple code and simple analysis of the brain. So I've talked a lot about biology, brain, neurons, and everything. Let's come to the engineering point of BCI. So first of all, there is a big myth that it's for the biology people, and people coming from engineering side or any different aspect can't contribute to it, and that's completely wrong. So if you see the different problems that BCI is facing from the engineering point of view is hardware. So whenever I put an electrode on my head, I'll probably move my head throughout the day. I'll probably talk to people, and on moving my head, the electrodes shift. And as soon as the electrodes shift, they record the wrong data. They record the data from the wrong part of the brain, which is completely useless to us, because that's not what we were targeting. That's not at all we were targeting. So find a way how electrodes stay at their place is a very big problem, and that's why Neuralink is trying to implant it inside your brain and not keeping it on your scalp. That's the major reason that Neuralink is doing that. Then comes from the data engineering point of view. As I told you, the amount of data that we get. Let's say you are doing a 16 channel. You have placed 16 electrodes from on your head, and you are capturing data 256 data points per second. That's like GBs of data in 10 minutes. Huge amount of data. How do you even read that into a file? How do you just visualize that kind of data? And that's the data engineering point. And now comes the data analysis. So previously I mentioned how information rich the data is, and in some cases that's really, really bad. Because let's say I want to detect what effect I have on my brain when I'm seeing a color red or seeing a color blue, or I'm reading Atlin for that matter. I am not concerned about my eye blinks. I'm not at all concerned about my heartbeat. I am not at all concerned about my hand movement. But that's also the information that is encoded in the brain waves. And to able to distinguish that information is a really big deal. And that's what the frequency part comes into play. If you can specifically decide what kind of frequencies is concerned when I'm thinking red or thinking blue, you'll be able to isolate that. you'll be able to tag that. It will be just like a simple tag that you put on different things to recognize that. It would become as simple as that. But obviously, there's not just frequency, there are different features like energy based features and features related to biological aspects of your body at that moment. Like, were you sitting, were you standing? Even that affects your brain signals. So that is the kind of information that we are trying to solve for when it comes to the field of BCI, brain-computer interface. So how does Python come into play? First of all, Python is pretty simple to understand, and that's a very big aspect when you're bringing new people to a community. If they're feeling comfortable, it's really nice. Again, the community that the Python language holds, it's really able to contribute to the massive amount of data that we have. Again, scalability is something that Python and different libraries concerned with Python are solving, and hence the issues with data engineering will get resolved over time. And visualization is also a very important factor, which I'll be showing you in some time. And how visualization of the data helps you is a very important factor. Cool. Let's come to the coding part. So here you'll see the data directly from my brain that was recorded from 2009, early 2019 as part of my research project. So this is a simple import. This part is a simple importation of the library, and generally you'll see data for EEG in form of EDF or CSV or MAT files. MAT is something related to MATLAB. So MATLAB is also a very nice tool if you don't want to pick up Python and you want to pick something that's really easy and is graphical user interface. Then I think MATLAB would be a very nice option to do that, and also it handles a huge amount of data very well. So in Python, the breakthrough in BCI came to the normal open source community when MNE was released. So MNE helps you do all sorts of processes that you might need in analysis of EEG, which is data, pre-processing, visualization, connectivity, machine learning, and statistics. So I hope I'm able to bring that point that ML or DL or fitting up models is not something that BCI is about. It's just about analyzing the data. Developing a model is still an easier part than getting the clean amount of data. So I hope I'm able to bring that out. So here what I do is I have an EDF file which is my data recorded while I was resting, and I read that using MNE using a simple read raw EDF file, and this is the amount of meta information that I have, which is the number of channels that were recorded, the time for which it was when it was recorded, the average time when it was recorded, and everything. So now I'll introduce you to a small fact, biological fact. You see these points that you see, and if you see at this portion, this is the nose, apparently, and these are the ears. And this is the placement of the electrodes. So this is a standard way of placing electrodes on different parts of the brain to capture different aspects of the brain. And if you see all the channels that are listed in my when the data was recorded, I have so many channels. And if you see, most of them are not listed here. For example, you don't have a sync channel, you don't have a CQP9 or anything like that. What you actually have is the top 14 channels, which I'll be showing how we're going to analyze or at least visualize for that matter. And okay, so what we need to do, yeah. So if they're placed on the same portion, it only depends upon the quality of electrode that device provides you. But the positioning is generally the same because they're focused towards extracting the main aspects of your brain. So yeah. Yeah, yeah. Yeah, so these are the standards. So these are the standards 128, 128 or 64. I'm not. I don't remember exactly. What's the exact number of? So these are the standard places where you place the electrode to capture every minute detail. Now, most of the devices can't incorporate all that data. I think you might have used Emotive or OpenBCI. Yeah. So these are not able to incorporate all the electrodes inside your brain, and hence what you need is a small number of EEG channels that capture the maximum amount of data for your brain, and which were these signals in my case. So these were the portion of the brain that I was focusing on. And if you see on this chart, let's say we go for AF3. AF3 is this. AF4 would be here, which would be the last. Yeah. So these are the different positions that I'm capturing for my brain. So M&E even provides you all the positions as part of its package, and it's a simple visualization of what M&E provides you. And when I map that to my data, I'm only able to boil down to the electrodes that have been recorded for me. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 electrodes at different positions to capture data. And these positions are very important when we capture emotional data. Now, this information obviously comes from doing literary research or reading people's work from the previous past. But yeah, you can boil down to which aspect of the brain you want. For example, the electrodes on the top two also capture eye movement, which we actually saw in that video that only two electrodes were moving while other electrodes were stable. So those were these two electrodes that captured the eye movement. Eye movement. Now this is the havoc that my brain looks like. This is a very small part of the recording. The recording were done for hours and hours. Now coming back to the frequency, as you might have recalled, I explained about the frequency things. So we are trying to analyze how my brain works in these different frequencies. So first any data you get, every time you get any data, you have to pre-process that data. So in general, what the limit of the data is people analyze the brain waves generally between 0 to 100 frequencies, because if any frequency that goes beyond that is generally is an outlier, unless and until you are analyzing data for epileptic seizures or Parkinson's disease, because in that case your brain goes completely haywire. So you limit to 0 to 100 or 1 to 100. For the demo purposes, I have limited it to 1 to 40. What right now is happening is that all of the brain data is converted into a frequency domain. All the portion of the brain that was above 40 frequency, or the waves that were associated to above 40 hertz is removed, and the data is converted back to time series data, and you get this thing. Now, if you, I'll restart it so that you can see what the difference it was in the data. Yeah, so if I zoom, you'll see the data that you see right here is very dirty. Very dirty, as in there's a huge rise up here from P7, and there's a huge drop from P7 right here. And it does not look of a clear pattern, and that's because of the noise that the data contains. And when we do this filtering, you can see how clean the data becomes. Now the P7, when it was reduced from all the frequency that it had to 0 to 40, you can see how less wavy the pattern for that brain wave is. Now I mentioned the alpha waves, the beta waves, the gamma waves. How you get that? So from the brain data that you have recorded, you again limited the time series data to those particular frequencies. So now coming to the independent component analysis. So when I was explaining you through all this, you might have heard me saying that we have a lot of information and we don't want that when we are analyzing data. So when I'm analyzing for emotion, I don't want to see the data that comes from my eye or data that comes from my heartbeat. And that's where independent component analysis comes into play. So every wave can be divided or is composed of other smaller waves. And these smaller waves, if you are able to divide the constant parts of that wave, you can remove the aspect that was considered to a particular aspect. So, yeah. So if you see the whole brain data that I had for a small clip, these are the small components of the brain. Now the part where it is red, again, similar thing is followed. The pointy thing is the nose, while the two lobes are the ears. Now, if you see which part of my brain is active when and which part corresponds to what, and this is the different components that have been extracted from my brain waves. Now, a very cool insight from here that, as I mentioned, that when a person is blinking, his electrodes in the front part of his brain are getting triggered, and I don't want that. And as you see, ICA0 is corresponding to that. It's very high towards the front part of my brain. Now you just might say that ICA002 is 2, but you can see from the right side of my brain was also active, and hence removing that would remove a really important chunk of the information that was being captured from the right hemisphere of my brain, and hence we can easily remove ICA0 but not ICA002. And here comes the artifact correction part. So when I see the data, what I'll do is I'll remove ICA000, which corresponds to my blinking. There are also some aspects that corresponds to my heartbeat. If I'm able to detect that, and when I'm able to detect that, I'll be removing that, and that will not tamper to my general analysis, which I'm doing for emotion or for any other case right now. So M&E also provides you artifact correction, which is it automatically understand what part is active at a moment, and it automatically removes. So it has now automatically removed some part of the brain waves after disintegrating into components, and it has regenerated the brainwave again for you. And it also gives you the analysis that what difference is there after the data has been changed. So red and black corresponds to previous data and the new data. So how the average across the EG signal has changed when you remove the artifacts. How is the raw data looking? How is the average across the channel? How was the raw data? So this is the kind of information you are able to detect. Now I mentioned that visualization is a very important aspect. Considering that the M&E library wouldn't be removing that for you, from this picture of your brain, you can very clearly understand that IC0 is corresponding to me blinking, and you can detect that and remove that aspect of your brain. And that's the analysis, the difficulty and analysis that M&E Python solves for you when it comes to data analysis or data visualization for that matter. So yeah, so that's a simple introduction to using brainwaves in Python, and that's how I'll be concluding now. So a very small thought that I want to put inside your brain is how can you make a blind person sense a color? So that's what people are trying to do. That's the level of information that you can see. For example, everyone here can recognize red color or blue color. If I'm able to map what I feel when I see a red color, and I'm able to affect a blind person's brain when I say the red color, he'll be able to have the sensation of red color without ever being seen. So that's the kind of impact that you can bring. There's always a very good API that will detect a red color and tell to the blind person that you're standing in front of red color. But to be able to make him sense that is what BCI is all about. Thank you. Yeah? What? BCI. So, so you're trying to imitate the brain, right? So they're a huge part of your brain that has still not been studied because it's so abstract. Because let's say if a blind person's auditory canal is provided information about vision, that auditory canal can detect vision also. So that's the variability in the brain. And to say that this part of the brain only deals with that aspect is the real difficulty. And that's why localization, so many electrodes, so many implants are being done. You understand? Yeah. So, okay. So let's say you have a lot of electrodes around your brain, and there will be some electrodes that will be placed just over your visual cortex, right? And there will be some set or a group of neurons that will be triggered when you see a red color or a blue color or any color for that matter. So you only take the data or isolate the data that is concerned with the visual cortex, and you see what difference happens when you see a red color and blue color. Yeah, it's been implemented. If you go to, I really advise you go to the John Hopkins page, and you'll see a huge amount of practical things that have been implemented and that have been done. So you can, even without doing anything, just thinking that a chair moves forward, you can even do that. Just because you're able to detect that aspect of the brain which thinks or which creates the thought process to move you forward. Yeah. Any other questions? Yeah. So, consumer behavior analysis. Okay. So first, what you need to do exactly is identify what kind of emotions or what kind of feelings you're targeting from a person, right? As soon as you're able to do that, you build a small device or a scalable device for that matter, which includes only electrodes at that position, which can be like a swimming cap because it's easy to wear, and you make them wear that. You put those electrodes at that particular position, and you record the data for that. And that's how you can imitate what person feels when he's excited or not. Any other questions? Yeah. So, if you are not looking to analyze your complete brain or even just trying to test it out, you can use Muse, which is available for I think 16 to 17,000. But the device that was used by me was Emotive. Emotive is one of the standards, and OpenBCI. These two are the standard consumer level hardware that you can get to analyze data, which almost mimic the data that you get medically. Yeah. So a huge amount of data is available on Kaggle. Specifically, Kaggle, there is American epilepsy data, which provides you data of a person when he's in a normal resting stage, when he's about to get epileptic seizure, and when he's actually getting epileptic seizure. And that data is freely available for you. And most of the research papers that have been used don't provide that data because they are specific to patients. But on Kaggle or UCI, you can get the data for free. Any other questions? Recording your own data. So there are medical facilities or NGOs. We can talk offline after that help you provide those devices on rental basis for simply saying, and you can record the data. But in that case, you have to maintain some clause, like you'll share your data to that person. You'll have to list down what all things you're going to do with the person you're going to record to maintain a proper standard. So that's there. Yeah. Anything else? Good. Thank you.